Welcome to class. You say thank you. I hope that you enjoy our class today, and we'll see if you can learn some things, right? So, we'll start off talking about what science means, okay? Science is different than just voting for the right answer, right? That would be like democracy or philosophy. Sometimes people say that philosophy is not just voting the right answer, but that's not always true. A lot of the time, philosophy is essentially groups of people getting together and deciding what the right thing to do is. Science is based on a different pattern, a different premise. This is how science works. First, you make an observation. You look and make an observation. Like this guy says, oh, look, it's a duck. And then you decide, if this is a duck, then it will eat some bread if I give it some bread. So that's called a hypothesis. You looked, you made an observation, and then you developed a hypothesis. And then you can perform an experiment based on that hypothesis. And the hypothesis generally introduces the experiment. It says, for example, because this is a duck, it's going to eat some bread. So I threw some bread at it, but the duck didn't eat the bread. So then I start the process over. I look again, I make a new observation, I collect the data, and I make another hypothesis or some more conclusions. I might say, oh, nuts, this isn't a real duck, it's just a duck made of wood. It's a wood duck, right? So then I said, well, if it's a wood duck, then if I take it and saw it in half, it'll be wood inside, right? So that might be another hypothesis that you make. This cycle of using experimental facts and different rules that you have come to understand to form hypotheses, or maybe you might call them theories, collective ideas, and then perform more experiments to make more scientific laws and find more facts. It's cyclic like this, in terms of you can go around and around again. And it's also repeatable. So somebody else on the other side of the world should be able to do the same thing and get the same results. All right? Enough observation, enough experiments leads to what we call models. Now, this is an example of a model. This little picture right here is the model of an atom. An atom. Atoms have, in the nucleus, there's a nucleus, protons and neutrons. You might have heard about those before. And then on the outside of the atom, you have electrons. Here's a little video. Let's watch this video of, whoops, this isn't the video I wanted to watch, so we'll watch that in a second. But this is a model of an atom. And this is one of the models of the atom that most people kind of think of and understand. This also used to be an early model of what an atom looked like, where you had your protons, the positively charged things, and the negatively charged things, which are the electrons, kind of floating together in a space. All right, this was what we call the plum pudding model. And it was kind of like you would think of this as a bowl of pudding with big chunks of plum inside it. And the plums were supposed to be the positive charges. But this is not the true, or is not the model that fits. Now, what we want to be careful of in science is thinking that the model is the only truth, because it's not the only truth, and it's not really how things actually are. It's just our model that we use to understand things. Now, a group of people wanted to make a really good model, because the better the model, then you can just look at it and you can know everything there is to know about it. If you can see the model and touch it and feel it and work with it, you can know everything you need to know. But there were some problems when they got together and tried to make a really good model. Let's watch this video of these people trying to make this really good model.
for more fun.
All right. So what do you think? What was that video trying to teach us? Any ideas?
Completely right?
Say that again. Sorry, I didn't have you turned up. Say that again.
Models always aren't completely like the other one.
Very good. That's right. Models aren't always completely right. Now, does that mean we shouldn't use models?
No, we should.
We should. They're helpful. They're very helpful for a lot of things. And without the models, then it becomes very hard to describe and teach each other and talk about what we're actually seeing. Okay? So, when we talk about things, when I say, oh, an atom is like a family with parents and children, or if I say an atom is like a ball on a string and the electron flies around, you have to recognize that these are models. And in your scientific life, if you find something that doesn't fit the model, that doesn't mean we throw it away. That just means that we have to recognize that our old model might have to be shifted a little bit. Okay, so once you have a model that's been around for so long, it can sometimes become a law, a scientific law. And generally when it's become a scientific law, then you get an equation, like this equation here where we have pressure being equal to a constant divided by the volume. Now this isn't an equation that you're going to memorize or want to know about at this point. At the end of the class, maybe we'll talk a little bit about this equation. But the thing we're trying to introduce here is that oftentimes scientific laws have equations associated with them. All right? Here's an interesting video here of oh, is this video not going to work for me today? It's not working. Well, we'll have to look at that one at a different time. Now, just because you're not thinking, oh, I'm going to be a chemist when I grow up, that doesn't mean that you should not try to understand the nature of the world around you. Because as you have an understanding of how matter, material, nature works, then you can improve your ability to help contribute in so many different ways. So never say, oh, I'm not going to be a chemist, or I'm not interested in chemistry, because these are natural laws. These are things that are true, and wherever you apply them, or wherever you are, you can't trick nature. And unless you understand the rules behind it, then you won't be able to change it or manipulate it in any way, which is what we do to kind of cure diseases, or to make better houses, or stronger cars, or less pollution, right? These types of things are only able to be done when we understand the natural world around us. One word that we're going to be using quite a bit is the word matter. Matter. And matter is a really general word. It means basically anything. Anything that has mass. Now, mass. What is mass? Well, it's just stuff, right? We kind of think of mass as, if it was on a scale like this, then you would get a number, and that's fine. That's mass. Now, sometimes people say, how much do you weigh? Right? Now, there's a difference between weight and mass. And we're not going to stress it a whole lot in this class, but you want to be aware of what the difference is. If I stand on a scale in my bathroom, and my bathroom says I weigh 600 pounds, my scale says I weigh 600 pounds, that's my weight. My weight. And the way that this machine, or the scale, took my weight is it has a spring inside it, and when I step on it, it compresses the spring, and the amount of compression relates to the amount of mass that I have. This is called a scale. There's also a way to determine my mass, or a different way which determines the mass, which is called a balance. A balance. A balance, you put the mass of two different things, so there I am, and then I have to have a balance, or a mass on the other side that weighs and has the same mass as me, right? And then will be balanced. Okay? This thing here is measuring my weight, whereas this thing over here is measuring my mass. Now you'd say, wait a second, it's 600 here and 600 there. That's the same. It doesn't matter. Weight and mass are the same. But if you go to the moon, make this smaller here. If I go to the moon and I have my scale on the moon, and I stand on the scale, do you know what it'll say? What do you think it'll say, Tom? 600. That's a good guess. But actually, because when you stand on the scale and it pushes the spring down, the amount it pushes down is dependent on the gravity that it feels. So on the moon, there's less gravity. It'll only say 100 pounds. 100 pounds. Because here's the Earth, right? And here's the moon. The moon is smaller, and there's a lot less gravity. Therefore, on a scale, I'll only have 1/6 the weight. So, here's my balance on the moon. There I am. What kind of mass should I put on the other side so that my balance works on the moon? What do you think, Tom?
600.
That's right. You still need 600. Even though this here has a big gravitational field, this is on Earth, this has a smaller gravitational field, and that smaller gravitational field is influencing me over here. So I still need this same mass. So a balance works independently of gravity, whereas scales like this will differ based on the amount of gravitational field that there is. Okay? So what do you think? Here's the question. It's kind of a joke question. But does living on the moon make you lose weight? Do you lose weight when you go to the moon? What do you think, Tom? You don't get skinnier, but you actually do have less weight, right? So when we say lose weight, we kind of think like diet and stuff like that. So that's why it's just a silly joke of a question. Okay, very good. Now, again, there is a difference between weight and mass. And in this class, we're not going to stress it too much, but you want to gradually become aware of that. Some other words that we want to be familiar with. Okay? An atom. We talked a little bit about the atom already. This is our model for the atom. Let's see how well or how much you've heard before. You don't need to have known this, but let's just see where you're at. Do you know what the middle part of the atom is? Nope. The middle part is called the nucleus. The nucleus. Have you heard of the nucleus before?
Yes.
Excellent. And the little ones that fly around the outside, do you know what those are called?
Electrons.
Those are electrons. Very good. So, electrons. Let's see if you know what the small particles inside the nucleus are called. What are the two kinds of particles that I have in the nucleus? Do you know?
Protons?
Yeah, we have protons and we have neutrons. Protons and neutrons are what are in the nucleus, whereas the electrons are on the outside. Do you know which of these three, protons, neutrons, or electrons, do you know which ones have positive charges? The protons have the positive charge. That's right. The negative charge, do you know which one has the negative charge?
Does electrons and neutrons have it?
Actually, just the electrons have the negative charge, whereas the neutrons have no charge. They're neutrally charged, we say. Okay? So the protons have a positive charge, the electrons have a negative charge, and the neutrons have a neutral or no charge. So this is the model of the atom. All right? Here's another, well, it doesn't look like that video is working either, but that's okay. So this is our model of an atom. Now, when you bring atoms together, so this, let's say, is an atom. It's a small atom. It has one proton and one electron. But then I'm going to bring it close to another one just like it. One proton and one electron. I'm bringing these close together. And then what happens is the protons get close enough that the electrons can now kind of go around both of them. So I have an atom here and an atom here, and I bring these atoms together to form a molecule, or we can call it a compound. A compound. A molecule or compound. So when you bring atoms together, you form molecules or compounds. And this is a very simple molecule, right? I just have one atom with one proton, one atom with another proton, and I brought them together, and now I have a molecule. But molecules can be very complex, like this black, red, and white one here. Each black atom represents a carbon atom. Each red one represents oxygen. So bringing atoms together forms molecules, and this atom or this molecule here is, pretty complex. Lots of different kinds of atoms and organized in a specific way. This over here is a molecule of DNA. DNA is a molecule. And now, I don't know if you know anything about DNA or have heard that before, but it's a really big molecule. So molecules can be really big. All right, but what molecules are combinations of atoms. Compounds, also a way to describe a combination of different atoms together. An element is a substance, a material, that only has one kind of atom. Only has one kind of atom. And we have so there are lots of different kinds of elements. And we have what's called a periodic table of elements. And I want to show you a periodic table of elements here. Whoops, that's not the one. Where's my periodic table of elements? So here's my periodic table of elements. Can you hear me now?
Yeah, but you froze again. Oh, you're moving.
Okay. So here we are. This is a table called the periodic table of elements. All the elements that exist in the universe, everywhere and beyond, are on this periodic table. So you can think of it as the Legos, all the different kinds of Legos that exist in the world, and everything we're going to be able to make, or everything that occurs, all reactions, all changes, is because of the interaction of different sets of these elements. All right, these Legos, these elements. Okay? And if you look at the elements on the periodic table, so for example, let's look at this one here. Hydrogen, the 1 right here tells us how many protons and electrons are in an atom of hydrogen. So this is an atom that's called vanadium, an element called vanadium. How many protons are in the nucleus of vanadium, Tom?
23.
That's right, 23 protons, because that top number tells us the number of protons that are in the nucleus of vanadium. So here's another question. If I have an atom and it has 28 protons in its nucleus, what's the name of that atom?
Nickel.
That's right, nickel. 28 protons. It must be an atom of nickel. All right. So we differentiate the atoms by the number of protons that they have in their nucleus. All right. And if the atom is uncharged, then that means it has the same number of electrons as protons. So let's see if you understood that part. I have an atom of nitrogen, and the atom of nitrogen is uncharged. Can you tell me how many protons and how many electrons are in my atom of nitrogen?
Oh, 14?
Nope. 7 is the number of protons, and 7 is also the number of electrons because it's an uncharged atom. Does that make sense?
What's an uncharged atom?
Uncharged atom is an atom that has the same number of protons and electrons. Okay? So, here's an example of my atom, right? I have 1, 2, 3, 4, 5, 6, 7 protons in it, 7 positive charges. And so with those 7 positive charges, I also need 1, 2, 3, 4, 5, 6, 7 negative charges. So the number of positive charges is the same as the number of negative charges, and that makes my atom uncharged. No more positives than negatives. It's exactly the same. So if I have 7 positives and 7 negatives, the result is no charge. Can you see that? All right. So what kind of atom is this if I have 7 protons in the nucleus? What kind of atom is this if it has 7 protons in its nucleus?
Nitrogen.
That's right. It's an atom of nitrogen, and N is the symbol. So that's how the periodic table helps us out. It helps us identify how many protons, how many electrons if it's uncharged, and we also have symbols to help us. And we'll talk more about that as well. So, when we talk about elemental material, or a material, its element, it means that all of the atoms are the same. So this is gold right here. And we can look on the periodic table, and we can look around and try to find it. Here it is right here, gold, 79. 79 protons in the nucleus of every gold atom. Sulfur, can you find sulfur on the periodic table? Its symbol is S.
Oh, 16. It's under the O.
That's right, 16. 16 protons. Very good. And diamond is made of carbon. Carbon has 6 protons in each element. So sometimes materials are elemental. That means all the atoms are the same element. Okay? When things are compounds or molecules, that means that it's a combination of different kinds of atoms. Okay. So, our chemical symbols. Our chemical symbols. These are just symbols that we've kind of invented to help us refer to atoms quickly, effectively. Carbon, C, calcium, Ca, bromine, Br, right? Nice and easy. We also can write these chemicals into what we call formulas, chemical formulas, like water. Have you heard of water before? H2O?
Yes.
And carbon dioxide. Have you ever heard of that one before? CO2?
I've heard of carbon dioxide, but not CO2.
All right, so CO2 is the chemical formula for carbon dioxide. And from that, if I write CO2 here, can you tell me how many carbons there are in one molecule of CO2? How many carbons do I have?
2.
No, that 2 is for the oxygen. But how many carbons do I have? Just 1 carbon. Can you see that?
Oh.
But the 2 is for the oxygen. So, let's look at water. Here's water, H2O. What does this molecule look like? How many atoms of hydrogen and how many atoms of oxygen?
1 atom of oxygen and 2 of hydrogen.
Very good. Excellent job. Okay. So, some of our elements on the periodic table are based on their Latin names. So you'll see some like sodium, its symbol is Na. Potassium, K. Iron, Fe. All right, and that's because they were named before English was the primary scientific language, and Latin was the primary scientific language. And so you have all of these different old elements that were discovered by us early on, having different chemical symbols. Okay, so gold, Au, aurum, right? Old names, but that's why sometimes the chemical symbols don't correspond well with the name in English. All right. So, I think that's a good place to stop for today. Does that sound good?